think, yeah, here we are. Okay. The clock on my computer is running just a little bit slow, but I think today I was able to counteract it. So welcome back to MAC1140 Pre-Calculus. Yesterday we finished up our section on exponentials and logs. We talked about uh, logarithmic equations and exponential equations. Those are what they sound like. Um, Today we are going to begin talking about systems of equations. Some of what I'm going to say today is sure to be a review from algebra classes of yore, but some of it may be new, some of it may give you a new way of thinking about some things that you've seen before. And I may ask you to kind of think a little more deeply than your college algebra professor did, so that we might then abstract and move forwards. I'm also going to introduce some new notations. So today is a cool day for you guys because you get to learn these things that you can put on whiteboards and just scare the shit out of people with, called matrices, which are very, very fun. So today you are going to learn about matrices, and you will never think of the film the same way again. Now, there is one section that we haven't covered, that's on the syllabus there, and that's the modeling section, modeling with exponential functions. I went through the problems in the textbook for that, and honestly, none of them are anything other than what you saw in college algebra. So I don't intend to beat you to death with that stuff. It's just a few special cases of formulas that you've certainly seen before. And in the event that you haven't seen them before, I will briefly provide a little discussion. But really today is about systems. So we are going to chapter 10. This is your book puts it in 10.1 is the discussion there. So 7. I'm not going to talk about because decided vectors don't belong in this class. That's okay. All right, let's get started. This, as always, is MAC1140, which is pre-calculus. Today is the 29th of July. So today, I'm going to begin matrices. There is a new homework set up for you guys. The homework set on log laws, exponential, and logarithmic equations. It's not super duper long. It's a little shorter than most of our homework sets, but it is up and it is due on Monday. So be aware of that. Both homework 7 and homework 8 are due on Monday. Homework 7, I didn't want to make that due yesterday on Wednesday, like we normally would have it, because you guys have that exam on Monday, and I know it can kind of take a little bit to get back up to steam or back up to speed after that. So you do have until Monday for homework 7, and then homework 8 is going to be due at the same day. It would always be due according to our schedule, which is Monday as well. So just be aware, 2 homeworks due on Monday. Maybe I'll take note of that here.
Are we going to have another quiz, or will that just be the exam? Is that going to be the last assignment?
I will do another quiz before our last midterm.
I also have a question about the horizontal line test.
Sure.
So in my trig class, the teacher, he uses the vertical line test, and I was just wondering, like, is there a difference? What's the difference between vertical line test and horizontal line test?
Good question. Yes, there is a difference. So the vertical line test is a test to see whether something is or is not a function. The horizontal line test is a test to see whether a function is or is not one-to-one. So for example, here's a graph of a relation. But this relation is not a function, because if you take any vertical line here, it penetrates that graph more than once, right? I mean, in fact, many, many points. Another example here would just be, let's do something simpler, stay away from the trig. So the red curve here does not represent y as a function of x. The red curve is not a function because there is a vertical line that hits it more than once. So that's the vertical line test. It says if any vertical line hits your graph more than once, then you're not a function. On the other hand, the horizontal line test says if any horizontal line hits your graph more than once, then that is not a one-to-one function. So when we talk about the horizontal line test, we're always kind of assuming that the thing we're looking at is a function. And we want to know, is that function one-to-one? Is that function invertible? So in the context of trigonometry, we see this when you're trying to cook up the inverse of a trig function, like the inverse of the tangent function. And here you see pretty much any horizontal line will smack the graph of the tangent function, not just once, but many, many, many times. And the way you fix that is by restricting the domain. So if I want to define an inverse to the tangent function, I restrict its domain to the interval -pi/2 to pi/2. And now, no matter where you draw a horizontal line, it'll only hit that graph in one place. And that's what allows us to define the inverse tangent function, which looks like this. So the original function being one-to-one corresponds to the inverse relation being a function. There is a connection between the two. But the vertical line test asks, are you a function? The horizontal line test asks, okay, function, are you one-to-one? So they're different tests. And that's the basic thing. The upshot, the big deal in trig is that just like here when we had to like throw away half the parabola to find its inverse, in trig you have to throw away quite a lot more because this thing without the domain restriction is very much not one-to-one. Right? If I compare the red and the blue is super duper not one-to-one, but the red is. So the red has an inverse. And the red does the same thing the tangent function does. It just, only has this small domain. We do the same thing with sine. Sine, if you restrict it, looks like that. Sine, if you don't restrict it, looks like that. So this is, again, not one-to-one. So if we want to invert the sine function, you got to restrict its domain. And now this is one-to-one. So yeah, inverse trig is a big deal. If you're looking for a place to get comfy with inverse trig, after this, I'm going to stop talking about this stuff so we can. This is my favorite resource. As I have students come to me in Calc 1 that are woefully unprepared to deal with inverse trig functions. If you're worried that's about to be you next semester, check out this page. It's really good. It's got the definitions, all the things people do wrong, problems with nice step-by-step solutions. It's great. Okay, so homework 7 and 8 due Monday. Today, we're talking about systems and matrices. We're not going to talk about the modeling section. I'm not an engineer or a physicist. I'm a mathematician. I'm here to teach you guys mathematics. But the section on exponential models, just like half-life problems and doubling time problems, same stuff you saw in college algebra. I'm going to omit it so that we can spend some proper time on systems and matrices. Okay. We're going to begin talking about systems with two variables. This is section 10.1. So a system of equations is a set of a collection of equations meant to be solved simultaneously. A 2x2 system of equations, or a system with two variables. So this is two equations with two variables meant to be solved simultaneously. Simultaneously, right? I'm missing an I. Oh, that's not one. They look like this. Maybe you've got 2x minus y equals 5, and x plus 4y equals 7. And the basic idea is you want to find an ordered pair call it x naught, y naught, that satisfies both equations. So when I plug x naught in for x and y naught in for y, the first equation is true. And if I plug x naught in for x and y naught in for y, the second equation is true. So both equations are true simultaneously. That's the goal.
Professor, what does the second word say? It says find what?
Ordered pair. Ordered pair. So we're looking for an ordered pair that satisfies both equations at the same time. There's two basic ways to do it. Substitution and elimination. Substitution. Boo. No good. No good. Substitution is just the worst. If you've solved these in the past using substitution, that's fine. Nothing wrong with that. But you will see, shit, this fucking duck can. You'll see that substitution is really an inferior method. As the systems get larger and larger, instead of having 2 variables, having 3, 4, 5 variables, the substitution method very quickly becomes a horrible idea. It gets very, very messy. But what doesn't get messy is elimination. Hurry up. There we go. All right. So substitution, no good. Elimination, we like this a lot. And on your exam, I will be asking you to solve your systems by elimination, not by substitution. Geometrically, what's going on here, when we say we're going to find a solution to the system, really what we're finding is a point that's on both lines. So, right, this is a linear equation, and this is a linear equation. And the systems we're going to play with are generally going to be linear systems. We're not going to play with nonlinear systems because those are horrible. Some of them you can handle, but in general, nonlinear systems are just out of whack. So if I graph each of these lines, this first guy I could rewrite as y equals 2x minus 5. He looks, space for this, but he looks like this. This is the graph of equation 1. And the other guy, I could rewrite this as y equals -1/4 x plus 7/4. He looks like this. The point I'm looking for is a point that's on both lines. So this right here is our solution. And in this case, it's the point 3, 1. You can check. If you plug 3 in for x and 1 in for y, this is true, right? 6 minus 1 is 5. And if you plug 3 in for x and 1 in for y, this is also true because 3 plus 4 is equal to 7. So this ordered pair, if you plug in the x and the y, solves both equations at the same time. Solving one equation means it's on the one line, and solving the other equation means it's a point on the other line. So geometrically, again, what we're looking for is an ordered pair that's on both lines. And that geometric understanding will help us kind of classify systems. Substitution. How do you do substitution? You solve one of the equations for one of the variables, then you plug that into the other equation. That'll get rid of that variable in the second equation. So you can solve for the other variable and actually get a number. Then you take that and plug it back into the first equation, and then you get both numbers. I'm not even going to go through it. I'm sure you've seen it before, probably since middle school, and boo, we don't like it. It's messy. Elimination is wonderful. So I will show you how to do this. The steps for elimination, you're going to multiply one equation by a constant, not zero. Don't multiply the whole equation by zero, that's no good. Such that I've chosen such that the coefficient of one of the variables becomes the negative of the coefficient of that variable in the other equation. All right, this is your first step. Then you add the two equations. So first, I'm going to multiply through one of these equations, it's up to me, by some number such that the coefficient of one of the variables becomes the negative of the coefficient of that same variable in the other equation. For example, if I multiply through the second equation here by the number -2, then I would get -2x minus 8y equals -14. It's the same equation, right? You can always multiply on both sides by an equation, of an equation by a number. Same equation, but now the coefficient of x here would be -2, which is the negative of the coefficient of x here, which is +2. If I wanted to, I could also multiply through the first equation by 4. I could do that instead. You don't do both, you do one or the other. If I multiplied through this first guy by 4, I'd get 8x minus 4y equals 20. So then the minus 4y and plus 4y, those would be negatives of each other. The reason we do that is because the next step is to add the two equations. So if I had like a -2x here and a +2x here, and I add those, the x's will go away. That's why we call it elimination. So you carefully choose your constant in step 1, such that when you add the two equations, one of the variables goes away. Add the two equations, which will eliminate or eliminating the variable. And then you solve the resulting equation. Resulting equation. And then finally, you do what's called back substitution. Back sub, aka plug in, and find the other variable. All right. So I'm going to show you what that looks like for this system. So I'm going to take my system here, and I'm going to do what I said. I'm going to multiply the second equation by -2. The first equation I leave alone. So it stays 2x minus y equals 5. But the second equation I multiply through everywhere by -2. So I get -2x minus 8y equals -14. That's step 1. Now I add the two equations. 2x plus negative 2x is 0x. Negative y plus negative 8y is negative 9y. And 5 plus negative 14 is negative 9. So in other words, I get negative 9y equals negative 9, which tells me, oh, y has to be 1. Now I'm almost done. I just back substitute this into either equation. So I've got x plus 4y equals 7. So x plus 4 times 1 equals 7. So in other words, x plus 4 equals 7, so x has to be 3. That's it. So my solution is the ordered pair 3, 1. Not so bad, right? The reason I keep writing the words ordered pair is because it kind of looks like an interval, and I want to make sure you're not confusing it with interval notation. Of course, the open interval from 3 to 1 would be empty, because 3 is bigger than 1. It's ordered pair. All right. Can I see just reacts in Zoom if you if this is completely let's do the other way. Reacts in Zoom if you have seen this before, solving systems of equation by elimination. You give a thumbs up, a wave, whatever you want. Okay, about half of us. Maybe a little more than half of us. Cool. So solving a system by elimination, not terribly hard. The ways these things can get fucky are if you know, you introduce some fractions. If I've got gnarly fractions in here instead of nice whole numbers, figuring out the arithmetic can be a bit of a challenge. The thing I would like to emphasize from a strategic standpoint is that you must be very careful at each step, more so than with the other problems we've done, because especially once the systems get larger, this process can get quite long. And if you make a mistake in step 1, you won't discover it until the very end. And then you'll be like, fuck, I gotta do all this again. And it's frustrating, believe me. I remember when I took linear algebra in college, sitting at a picnic table at UF trying to solve some systems and discovering for myself, again, just how careful you need to be. Just put it nice. All right. So solving a 2x2 is not terribly hard, but not every 2x2 can be solved. Let's do 2x minus y equals 1 and negative 6x plus 3y equals 0. And of course, when I say solve a system, here I mean by elimination, not substitution. Never substitution, always elimination, always. So what variable do we want to eliminate? You tell me. You want to get rid of the x's or the y's?
Would it be easier to do y's?
Let's do the y's. So I've got a negative y up here and a positive 3y here. So if I multiply through this equation, the first one, by 3, I'll have negative 3 and positive 3, right? So second equation, nice thing to do, copy down the stuff that doesn't change first. I'm not changing the second equation, so I'll copy it down first. And now if I multiply through the first equation by 3, I get positive 6x, 3 times 2x, minus 3y equals 3. Multiply everything back. And then add the equations. 6x plus negative 6x, the x's also go away. 3y plus negative 3y, and 3 plus 0. Well, 0 times x is definitely 0. 0 times y is definitely 0. So what does this say? This says 0 is equal to 3. But 0 is not equal to 3. This is called a contradiction. Mathematical notation for that is usually 2 arrows like pointing at each other. Contradiction. And what's going on here is when we run through this procedure, we're kind of assuming a solution exists. The solution doesn't exist. If you graph these two lines, the first one is equivalent to y equals 2x minus 1. And if you solve the other guy, you get y equals 2x. So you've got two lines here. I'll do them in colors. So the bottom one is just y equals 2x. It's a line through the origin, a slope 2. And the first guy is 2x minus 1. So you see from the geometric perspective that there's no solution because these lines are parallel. So they never touch. And remember, the solution to your system is the point that's on both lines. So if those lines never touch, then there is no point. Which lies on both lines. i.e., the system has no solution. There is no ordered pair that sits on both lines. Okay. So it's possible for a system to not have a solution. And you will discover that during your elimination by reaching a contradiction. Something like 0 equals 1, or 0 equals 3, or negative 5 equals 7. It's not always the case that just because the left-hand side comes out to 0, just because you get 0x and 0y, that you will be in a contradiction. If we had 0x plus 0y equals 0, that's sort of the opposite of a contradiction. That's true no matter what you plug in for x and y, and those are called tautologies. So if I modify this system just a little bit, well, let's do something maybe a little bit different. 1/2 x plus 3y is 0, and negative x 6y. Here's another system. Again, I'd like to multiply one of the equations by a constant, add it to the other. and I want to choose that constant so that one of the variables goes away, I could multiply through this first guy by 2, because 2 times 1/2 is is 1, and that would be the negative of this. So I'll start by multiplying the first equation by 2. Also has the benefit of clearing the fraction. And I leave the other equation alone. And now when I add, I get 0x plus 0y equals 0. And this is true, so this is true regardless of our choice for x. It's called a tautology. A statement that's true kind of regardless of the values of the parameters is a tautology. What this means is that the two lines are actually the same line. Maybe they're slightly disguised, but they're actually the same line. In this case, it's y equals negative 1/6 x. Looks something like this. And they are, in fact, the same line. So again, they're parallel, but it's deeper than that. They're the same line. So every point on one line is automatically on the other. I want to be clear. Just because this reduces to a tautology does not mean any ordered pair XY satisfies the system. So, for example, right here, this would be a solution. This would be a solution. In fact, there's infinitely many points along this line. So there's infinitely many solutions. But this right here, this point, this is not a solution. All right, this point is sure as shit not on both lines. It's not on either. It's just that any point that's on the one line is automatically on the other. So it's true here. Let me come back here. So in the previous example, we saw no solution, right? Here, what we get are infinitely many solutions. But again, that doesn't mean any ordered pair is a solution. So how do you say whether a point is a solution or not a solution? First, the logic thing there can take a second, right? If there's infinitely many solutions, then shouldn't every ordered pair be a solution? No, not necessarily. Right? There's infinitely many whole numbers, but not every number is a whole number. Just because there's infinitely many of something doesn't mean everything is that type of thing. So in the previous example, I can stop. Contradiction, stop, no solution. In this example, we get a tautology, but I don't just stop and say there's infinitely many solutions. You need to tell me what the solutions are. But of course, you're not going to be able to write out a list. You can give me one solution, that's fine. but that's not all the solutions. And you certainly can't write down all the solutions one at a time. So you need some way of characterizing the solutions. So here's what we'd say. We would say the solution set is all ordered pairs on the line. Now, how do you characterize those things algebraically? Well, it's all the ordered pairs on the line. What's the line? The line is y equals negative 1/6 x. That's the whatever standard form, mx plus b version of this line. So what does all ordered pairs on that line look like? Well, it's all the ordered pairs of the form x comma y, where y is negative 1/6 x. So I'd say that this is x comma negative 1/6 x. It's the set of all ordered pairs of this form such that x is any real number. And sometimes you'll see this in your homework. The book likes to use the letter T instead of the letter X, just to emphasize that it's, they'd say, a free parameter. So you'll see this written as stuff like T, comma, negative 1/6 T. And then the statement on the right here, there is a nicer way to say is any real number. You can just say T is an element of the real numbers. So notation here. R, with that extra leg on the side, this is the set of all real numbers. The notation here is called Blackboard bold, and there's other ones. C is complex numbers. Z is the integers. N is the natural numbers. You know, this is sort of the nicest way to write down the solution to this guy. So things I want to really drive home that I don't always get through in college algebra. Just because there's infinitely many solutions doesn't mean every ordered pair is a solution. Boom, right here, this point, the ordered pair that I've drawn right here is not a solution. So there's infinitely many of them, but you need to know how to tell me what they are. Giving me one or two is okay, but what I really need is the set of all solutions. If you write it like this on a test, I'll be 100% happy, dope, good job, perfect score. Your homework, you'll see it like this. They mean the same thing. The ladder notation has some advantages when we get into higher order systems. Okay. So a system of linear equations can have a unique solution, one point where the lines cross. Can have no solution if you have two parallel lines that don't touch, like same slope, different y-intercept. Or they can have infinitely many solutions if they happen to be the same line, meaning same slope, same y-intercept, if you choose to think of it that way. That's true of linear systems in general. So regardless of whether we're talking about 2 variables or 3 variables or 10 variables, theorem, fact, oh, theorem. A system of linear equations will always fall in kind of either one, i.e. the word unique we like in math solution. Funny story again. Unique is not a quantifiable term. When I say this is like so unique or a little unique, that shit doesn't make sense. If something is unique, that means there's one of them. So if you want to impress mathematicians, use this word carefully. Unique means one and only one. It's possible that there is no solution. And it's possible that there are infinitely many solutions. Every linear system falls into one of these categories. The proof for 2 by 2s, you just saw it. Lines either touch once, touch never, or touch always. For 3 by 3s, 4 by 4s, it's a little tougher because there you're talking about equations of planes, which can like intersect in a line. They could be the same plane. They could be parallel planes. It's a little more complicated, but it's true in general, regardless of the number of equations, that every linear system always falls into one of these categories. I'll try to show you the geometry for the 3 by 3s. 4 by 4s and higher, I can't see a 4D graph in my head. I don't know about you. There's special names for these. If you have a unique solution, then we say that the equation, the rows are independent. So let me classify it like this. No solution means inconsistent. And technically, if you omit the right-hand side, we would say the rows are dependent, but your textbook just says dependent means infinitely many solutions. For those curious, the language here is linearly dependent, linearly independent. And if you have infinitely many solutions, it means the rows of the system, the rows of the matrix, are linearly dependent. And this guy, if there is a solution in general, we would say that the system is consistent and that the rows are independent. Your book doesn't care about that, so I'm not going to force you to learn it right now. Okay, but know that a system with no solution is called inconsistent, and that a system that has infinitely many solutions is definitely a dependent system. There are some fun word problems that you can solve with these. But again, modeling, I want to get to matrices. I want to get you guys to the good math, which means that's really all there is to say about 2 by 2 systems. So we're going to graduate to multivariable systems. This is section 10.2. Systems of linear equations with 3 or more variables. Here, in this context, using substitution really falls apart. All right, you can solve 2 by 2s with substitution. You technically can solve 3 by 3s and 4 by 4s with substitution, but shit goes so badly off the rails so quickly that you will see elimination immediately is the better tool. An example. Maybe let's see, a nice example, please. But I suppose first we're gonna give some definitions. The system is called triangular form. If it looks like this, I'll do the 3 by 3. X minus 2y minus z equals 1. Y plus 2z equals 5. And z equals 3. So when you write down a system, always line the variables up in columns. All the x's here, all the y's here, all the z's here, all the non-variable constant terms on the right. This is going to be an important organizational scheme as you solve systems by elimination. This is what it means. So in other words, kind of this is your main diagonal. And let me modify something here. Let me call this 3z equals 3, because the coefficients here, they don't need to be 1. We just want to see that all of the stuff kind of beneath this main diagonal should be 0. So the important thing here is that these are all 0, that there's nothing in here. This would technically be called an upper triangular system because all the stuff below the main diagonal is 0. All the non-zero stuff is above the main diagonal. So sort of this part right here. There's a term for this. This is called the main diagonal system. If everything below the main diagonal is 0, that's an upper triangular system. If everything above the main diagonal is 0, that's a lower triangular system. So this is an upper triangular system. Your book just calls it triangular. Solving these is easy. Just a fact. Can anybody see an easy way to solve this upper triangular system?
Could you simplify it to like 2 equations instead of 3?
Even better. This bottom equation tells me what z is right away. So I'll remember the equations 1, 2, 3. Equation 3 says 3z equals 3. So because the third equation only has one variable in it, I can solve that explicitly. That means z has to be equal to 1. And then you can substitute that back up into the next guy, because this guy only has 2 variables in it, and now you know what z is, you can easily solve for y. So if you plug z equals 1 into equation 2, you get y plus 2 times 1 equals 5. So in other words, y plus 2 equals 5, which means y is 3. Plugging both of these into 1, we see that x minus 2 times 3 minus 1 is equal to 1. So that's x minus 6 minus 1, x minus 7 equals 1. If x minus 7 is 1, then x is 8. So an upper triangular system is easy to solve because from the last equation, you can read off the value of the last variable. And once you know that, you can substitute up into the equation above to get the value of the second to last variable. And you continue that until you have all the variables. This works, if I wrote down a 4x4 upper triangular, a 5x5 upper triangular, then this would be the same deal. All right. This procedure is called back substitution. Right? It's the same thing that we did after eliminating one variable from our 2x2 systems. We back substituted into one of the other equations to solve for the other variable. Well, once your system is in triangular form, you can back sub all the way up. You solve that last equation for its one variable, and then you back sub all the way up the ladder. Okay. How do you take a system that's not in this form and get it into this form? That's the key. Because once you're in this form, it's very easy to solve. So what we need is a sequence of steps that will take us from a arbitrary system into a system that's in this nice triangular form. The good news is that a very smart man named Gauss figured out a nice procedure for this. It's called Gaussian elimination or Gauss-Jordan elimination. And it is the generalization of elimination, right? The same elimination we were doing for 2x2s, we can do for 3x3s and 4x4s. But that language I'm using, by the way, 2x2, 3x3, that means the number of equations, 1, 2, 3 equations, and the number of variables, 1, 2, 3 variables. So this is a 3 equation by 3 because there's 3 variables. So the big idea here is to take a general system and turn it into an equivalent triangular system. And the things you're allowed to do to kind of slowly transform the system from not triangular to triangular that allow it to stay equivalent, the things you're allowed to do to a system that don't change the solution are called row operations. All right. To transform, to manipulate, let's say, manipulate the form of the system. Without changing its solution. So I'm going to take a general system, I'm going to do some row operations to it. As long as I use only those kosher row operations, I won't change the solution. In the end, I'll have a triangular system whose solution is the same as the general system with which I began. What are these magical row operations that I'm allowed to do which don't change the solution set? Here they are. Row ops. First, I am allowed to add a multiple of one row or equation. You'll hear me starting to call the equations rows. Add a multiple of one row to another. But that multiple needs to be non-zero. Right, so I can multiply an equation by a number and add it to another equation. That's kosher. Turns out doing that will never change the solution of the system. Another thing you're allowed to do, you're allowed to multiply through any row or equation by a non-zero constant. By equation. Non-zero constant. If you multiply through an equation by zero, both sides just become zero. All you've done is nuke the information that that equation is encoding. So definitely don't multiply through by zero. That doesn't help. And then the other thing you're allowed to do is you're allowed to swap any two rows. All right, x plus y equals 3 and x minus y equals 0 is the same as x minus y equals 0 and x plus y equals 3. Just changing two rows, swapping two rows, that of course does not change it. So these are your row operations. Any of these. And the goal is to do these cleverly so that you end up with a triangular system because we know how to solve those. So I am going to now solve for you a 3x3 linear system by first transforming it into an upper triangular system and then back substituting. And this is the general procedure. There's a lot of writing here. I will show you a special notation I like to use for this. Special notation for row operations, but first let's write down the system. X minus 2y minus z equals, oh, sorry, plus 3z. Sorry. X minus y plus 3z equals 1. X plus 2y minus z equals 13. And 3x plus 2y minus 5z equals 3. There's a special algorithm. There's an order that you want to do things that will get this done for you. And that's that Gauss-Jordan elimination. The first thing you want to do, so I'll tell you this, the terms along the main diagonal are called the pivots. First thing you want to do, so this is the first pivot because it's the term along the main diagonal in the first column. In the second column, the term along the main diagonal is this guy, so this is the pivot in the second column. And in the third column, the term along the main diagonal is this guy, that's the third pivot. Very first thing you do is make the first pivot 1. It's this guy, the number in front of the x here. Now it's already 1. Then you want to nuke everything below him. So how do I make this a 0? How do I make this a 0? Let's start with this.
Multiply by 0.
Now remember, I'm not allowed to multiply by 0. Any constants I'm going to multiply by have to be non-zero.
-3.
So my goal is to make this guy a 0 using one of these operations. If I multiply through here by -3 and then add this guy to it, that will do it. But kind of here's the idea. Having each pivot be equal to 1 kind of lets you use that guy as a tool to kill everybody below him. So here's what I'm going to do. To make this 0, right, to get rid of the x here, I'm going to multiply this by -1 and add it to this. So we're going to do two things at once. It's just this first row operation. You can add a multiple of one row to another row. That's considered a single operation. As I do this, the only row which will change is row 2. Row 1 stays the same. Row 3 stays the same. I'm only changing row 2. I'm going to add a multiple of this row to this row. And the effect is that row 2 will change. So here's the notation I use. I put an arrow. And I say that my new row 2, capital R2, capital for new row 2 is equal to my old row 2, little r2, minus old row 1. So I'm multiplying old row 1 by -1 and adding it to row 2. You could say, if you want, plus -1 times r1. If we're being very careful about it, that's what we're doing. So I'm going to multiply my old row 1 by -1 and add that to row 2. That will be my new row 2. That's what this notation means, and it's a very useful notation. Again, you want to begin by writing down the stuff that doesn't change. So I'm going to write down rows 1, and row 3. It'll just help you keep your brain organized. Trust me on this. Write down the stuff that doesn't change first. What's changing? Row 2 is changing. My new row 2 is my old row 2 plus -1 times my old row 1. So I'm going to multiply this by -1 and add it to this. -1 times x plus x is 0. So this is gone. -1 times -2y is positive 2y. Positive 2y plus 2y is 4y. -1 times 3z is -3z. -3z plus -z is -4z. And -1 times +1 plus 13 is +12. That is the result of this first row operation. Take a second, make sure you see where everything's going. And I advise you to use this notation because otherwise you won't be able to, you go back and look at this shit, you'll be like, what was I even doing here? If you write this down, you'll be able to go back and check your work. So everybody see why this became 4y and -4z? -1 times this plus this. -1 times this plus this. Don't forget to do the right-hand side. A lot of people forget that. -1 times this plus this. And then remember the other rows don't change. Row 1, row 3, they don't change. I'm not multiplying row 1 by -1 and then separately adding that to row 2. I'm doing both at once. I multiply row 1 by -1 and add that result to row 2. All I'm doing is changing row 2. And I'm using row 1 as a tool to do it. Row 1 is my hammer. Questions on this?
So for row 2, you just added the -1. Is that correct?
To get this new row 2,
Yes.
I added -1 times my old row 1 plus my old row 2. So I took this guy and I added to it -1 times this guy. So imagine you multiply through this first row by -1. This guy would become -x. Add that to +x and you get 0. Multiplying through this first row by -1 would make this +2y. So +2y plus 2y is 4y. And if I multiply this by -1, I get -3z. -3z plus -z is -4z. And the same thing here. Yeah, so it's a little bit sneaky, but that's, again, why it's so nice to write this down. This encodes the process. That way, if you are unsure what you did, which believe me, it'll happen, you'll be like, what was I doing here? I do it all the time. You can look and go, oh yeah, and then you can check and make sure it's little arithmetic things on there. Okay. Remember my goal. I have this guy with a 1 in front of him. So my next step is to nuke everybody below him. I want to get everything below the main diagonal 0. So I need to kill this and I need to kill this. You clear out one column at a time. So I've got my 1 here. I've cleared this out. I need to clear this out next. So what row operation? I'm aiming to alter the third row. Because I want to kill this guy. He's in the third row. What's my row operation going to be? Where does my new row 3 come from?
Lowercase r3 plus -3 times r1.
Perfect. My new row 3 will be my old row 3 plus -3 times my old row 1. I'm going to multiply through this row by -3 and add it to this row because -3x plus 3x is 0. Now, you're going to see me starting to write this as just r3 minus 3r1, right? Nobody writes plus -3 times. So I will also stop doing that. But for now, rows 1 and 2 don't change. Only row 3 changes. So x minus 2y plus 3z equals 1. 4y minus 4z equals 12. Now, -3 times this plus this is 0. -3 times this plus this, well, that's +6y. -3 times -2y is +6y. Plus 2y is 8y. -3 times this plus this, well, that's -9z plus -5z, which is -14z. -3 times this is -9z. -9 plus -5, that's 14z. And then -3 times this plus this is 0. And now, underneath your main diagonal in the first column, it's all empty. This is good. We're on our way to being upper triangular, right? I need this empty and this empty. Here's my main diagonal. Once I get this gone, everything will be good. We'll be in our upper triangular form. After you finish out with a column, you move to the next column and its pivot. You want to make that pivot 1. So is there a nice way, something I can do to row 2 to make the pivot term here a 1, to make this a 1y?
Divided by 4.
Good. So this is the other kind of row operation. I'm just going to multiply through a row by a number. My new row 2 is 1/4 my old row 2. Divide by 4, multiply by 1/4. I'm just trying to use the language that we have for our row ups, right? Multiply by a non-zero constant. So rows 1 and 3 don't change. X minus 2y plus 3z equals 1. Here, multiply by 1/4, you get 1y. Multiply by 1/4, you get minus 1z. Multiply by 1/4, you get 3. And the other guy is still 8y minus 14z. Okay. Now I'm almost upper triangular. The only thing I need to do is nuke this guy. Once this 8y is gone, I'm in my good upper triangular form. I know I can quickly and easily solve the system by back substitution. So it's time for one last row up. I'm modifying row 3. So I want to get rid of this 8y. It's in the third row. In order to do that, I will multiply row 2 by -8 and add it to row 3. In other words, my new row 3 is my old row 3 minus 8 old row 2. That's the way I usually write these. Row 1 doesn't change. X minus 2y plus 3z equals 1. Row 2 doesn't change. Y minus z is 3. Row 3 now. I'm going to multiply this by -8 and add it to this. That's going to make a 0y there. -8 times -z is positive 8z. Negative 14z plus 8z is negative 6z. So multiply this by -8 and add it to this. -8 times -z is positive 8z. Positive 8, it's negative 14. 8 minus 14, it's negative 6. And then over here, I do the same thing. So I'm going to multiply this by -8 and add it to this. -8 times 3 is -24. And now this system is triangular. So we solve it using back substitution. Solve the last equation for z, plug that into the one above, solve for y, plug those both into the one above, solve for x. Bottom tells me -6z equals -24. That means z has to be 4. Now I'll sub z equals 4 into the second equation. I have y minus z, which is y minus 4, equals 3. So y is equal to 7. And then finally, I'm doing all of this with this system, right? Just using the space over here. Finally, I'll sub both 4 for z and 7 for y into this equation. And I'll get x minus 2y minus 2 times 7 plus 3z plus 3 times 4 equals 1. So what is that? That's x minus 14 plus 12 equals 1. X minus 14 plus 12, that's x minus 2 equals 1. So x is equal to 3. And that means that your solution here the solution to a 3x3 is an ordered triple. Three, 7, 4. Okay. So that's how you solve a 3x3. or a 4x4 or a 5x5. You use row operations to take the system as it's given to you and put it into triangular form, then solve using back substitution. It's not terribly hard. There's a meaningful amount of arithmetic. But if you're careful in each step, then it won't give you a hard time. I do want to show you the geometry. I think of anywhere I can get a good graph of 3D stuff here. So let me see what I can find. Yeah, here we go. All right. So neither of those are the nice case. Looks like it might be okay. Yeah. All right. So let me come back over here for a second. Looking at the original system, each one of these equations, like x minus 2y plus 3z, I can graph that for you here. You haven't seen this before. This is the equation of a plane, a flat thing in 3D space. Here it is. What we're looking at then, when we talk about three systems, each having three variables, this is even better, is how do these three planes intersect? I'm looking for a point that's on all three planes. A point in three-dimensional space is an ordered triple, x, y, z. If all three planes kind of have different, the word isn't slope, it's a normal vector. If all three planes kind of point different ways, and no two planes combine to give the third, then you'll be in this situation where all three planes meet at a point. Now there's lots of other possibilities. It's possible that all three planes are totally separate parallel planes. That's this possibility right here. If all three planes are totally separate parallel planes, then there's no point which is on all three of them. Therefore, there is no solution to that system. If all 3 points meet in a line like this, then you'll have infinitely many solutions, right? Every point along that line where they all meet, that's going to be a solution. It's also possible that all 3 planes are the same plane, right? They're all just sitting right on top of each other. And then it is possible that pairwise, 2 planes meet in a line, but without any point existing that is common to all 3. I'll see if I can find some sort of utility that lets you get in and zoom around and play with these, because I really feel like something like that should exist. Although I'm not sure it does. Yeah, okay, here we go. So here's one equation. Right, you can see, let me rotate this a little bit. Your x-axis is the black axis, your y-axis is the pink axis, and your z-axis is the blue axis. And so that green plane you see there is 2x plus 3y plus z equals 2. If I throw in the extra equation, negative 3x minus 3y plus z equals 0, you can see here that these 2 planes meet in a line. Everybody see that? The place where the green and the pink meet is actually along this line. Can I graph? It's just going to graph one point. Okay. If I throw in the third plane, all 3 points, look for one point that's on all 3 planes. It has to be along that line we were just looking at, because it has to be on both of those planes. but it also has to be on the blue guy. And if we toggle our intersection point on, there it is, right there. There's a point that is simultaneously on all three of those surfaces. Let's see if I turn this off, it's on the blue surface. If I bring the peach guy back, it's on both the blue and the peach guy. And then if I bring our original guy back, you see he's on that as well. So a little bit harder to visualize, and you can see why I'm saying the 4x4 case is harder still. Here's one plane. And here's another plane that meets that first plane along a line. And here's a third plane. And there is indeed one point where all three of those guys touch. I wonder if this would, these are all going to have unique solutions. So let's see, it looks like this might even be friendly to phones and stuff. So let me send you this. Play with it if you want. Here's a link to that applet. All right. So yeah, the 4x4 case is much harder to visualize, but all the same rules work. Again, you either have a unique solution, no solution, or infinitely many solutions. I'm going to show you one of each. How am I doing for time? Yeah. Show you one of each today, and then I'm going to introduce the notation that we're going to use to solve these things down the line. Basically, that organizational scheme where you put all the X's in one column, all the Y's in another column, and all the Z's in another column, you just stop writing the X's, Y's, and Z's, and you got yourself a matrix. But let's run through just a couple more examples here. So I want to solve the system. Here. X plus 2y minus 2z equals 1. I'll call that equation 1. 2x plus 2y minus z equals 6. I'll call that equation 2. And 3x plus 4y minus 3z equals 5. You'll notice some relationships between the third row and the first two rows. Look just at the left-hand sides. I don't want to spoil it for you, but there is a way to tell ahead of time if your system has a unique solution or not. And those who see the pattern comparing these two to this one may be able to start hypothesizing about what it means when I say dependent.
Are you mean how the positive and the negatives line up?
Well, so 1 plus 2 is 3. 2 plus 2 is 4. And negative 2 plus negative 1 is negative 3. So it's to do with the signs, partially, but it's more about the third equation being a linear combination of the other two. In particular, if I sum the first two, I get the third. It doesn't have to be that simple. But here, that's the thing that gives it away. But let's go ahead and proceed as though we don't know anything about this. I want to use my algorithm, the Gaussian elimination, to put this into triangular form and just see what happens. I want to nuke the 2x down here, so my second row is going to be my old second row minus 2 copies of my first row. That'll do it. So row 1 doesn't change. Pro tip, cross your z's so they don't look like 2's. 2x minus 2x is 0x. And here, so now I'm going to multiply this by -2 and add to this. That's going to give me -4y plus 2y is -2y. This times -2 is positive 4z plus -z is positive 3z. And this times -2 is -2. -2 plus 6 is 4. And the third row, oops, I broke my own rule. Write down the stuff that doesn't change first. It is possible to do multiple row operations at once. But I won't do that to you just yet. I will do 2 on a single line though to save some space. So now I want to kill this 3x. So I'm going to subtract 3 times my first row from my third row. In other words, I'm going to multiply row 1 by -3 and add it to row 3. So it's row 3, which is changing, and it's going to be my old row 3 minus 3 copies of my old row 1. So rows 1 and 2 are not changing here. X plus 2y minus 2z equals 1. Negative 2y plus 3z equals 4. And now I take this and subtract 3 of these. That gives me 0. I take this and I subtract 3 of these. That's 4 minus 6 is negative 2y. This minus 3 of these. 3 of these is negative 2z times negative 3 is positive 6. So positive 6 plus negative 3. 6 plus negative 3 is positive 3. So I'll have plus 3z here. And then negative 3 times this plus this is negative 3 plus 5 is positive 2. And if you kind of just look at these two, forgetting about the first equation, you'll see this is very similar to the 2x2 system we saw, which had no solution. Now you're thinking in terms of block matrices, which is good stuff. But we just keep doing like we're doing. So we cleared out all the stuff beneath x in column 1. Our next step would be to make this a 1 and then clear out everything beneath it. We don't actually even need to make this a 1 to clear out the stuff beneath it, though. Sometimes you can skip making the pivot 1. It's not the end of the world. If I just multiply this by 1 and subtract it from this, multiply this by -1 and add it to this, or subtract this from this, then the y's will go away in row 3. So my new row 3 is old row 3 minus old row 2. Rows 1 and 2 don't change. This minus this is 0. This minus this is 0. This minus this is -2. So you get down here just 0 equals -2. And that's your contradiction. So there's no solution. And you're done. If you reach a contradiction, then there is no solution. There's no solution for you to write down. You've discovered the truth. The truth is this system doesn't have a solution. In other words, there is no point that lies on all 3 of these planes. What's going on here is that the third row is a combination of the first 2 rows. So those first 2 planes, they meet along a line. And then that last guy is just totally separate from it, doesn't touch him.
If the third equation was equal to 7, would there be like all solutions?
Infinitely many.
Or infinitely many, yeah.
And that's the last thing we're going to look at here is a system with infinitely many solutions. So I want to solve x minus y plus 5z equals -2. 2x plus y plus 4z equals +2. And 2x plus 4y minus 2z equals 8. Here it's a little harder to see what combination of rows give you the other row, but it is again the case that one of these rows will be a linear combination of the others. Meaning, you multiply this by something and add it to the appropriate product, multiple of this, and you'll get this, something like that. Let's see what happens if I try to solve this. Again, I've got a 1 in the first pivot. So I go trying to clear out things beneath. So I'm going to clear out the 2x in row 2. To do that, I will say my new row 2 is going to be my old row 2 minus 2 copies of my old row 1. Rows 1 and 3 don't change. All right. If I take this and I subtract 2 of these, I get 0. If I take this and I subtract 2 of these, I get 3y. If I take this and I subtract 2 of these, I get -6z. And if I take this and subtract 2 of these, that's 2 minus, right, my arithmetic. So -2 times this is +4, plus this is +6. Do your arithmetic carefully. Double check yourself. -2 times this plus this is 0. -2 times this is 2y plus this is 3y. -2 times this is -10 plus +4 is -6. -2 times this is +4 plus this is +6. Okay. Next, I kill the 2x down here. So my new row 3, same trick, is my old row 3 minus 2 copies of my old row 1. We copy down the things that don't change. Row 1 is still x minus y plus 5z equals -2. Row 2 is going to stay 3y minus 6z 6. But row 3 is going to change. This minus 2 of these is 0. This minus 2 of these is 6y. Right? -2 times this is +2y plus 4y is 6y. This minus 2 of these is -12z. And this minus 2 of these is 12. And again, if you look at the last two equations, the sort of subsystem here, if you multiply this by 2, you get this. Not just on the left-hand side, but on the right-hand side also. So you see that when you go to kill this 6y, you'll simultaneously kill the 12z and the 12, giving you 0 equals 0 in there. Let's do it. My new row 3 is going to be, what do I need to do to this? Multiply by -2 and add. So it's old row 3 minus 2 old row 2. Row 2 by -2. Add to row 3. Rows 1 and 2 don't change. -2 times this plus this is 0. -2 times this plus this is also 0. So everything on the left becomes 0. Negative 2 times this plus this is also 0. Oh, shit. So 0 equals 0. This is a tautology. We have infinitely many solutions. But what are they? It's not going to be every ordered triple. You can't just go plugging random shit in here and expect it to work. It won't. Plenty of stuff will work, but not anything. And one of the interesting things you'll run into is how many independent rows are there. See, it's possible that you have 2 free variables. It's possible you have 1 free variable. Here we have 1 free variable because we only got 1 tautology. If it turned out to be the case that through our elimination process, 2 rows became all 0 at once, then you have 2 free variables. So what we do here is we choose to call the variable z, the variable whose pivot would be here, t. So what we're going to do is we're going to let z equal t be a free variable. Kind of just like we did on the 2x2 case. I said x is a free variable. I gave all the solutions in terms of the variable x. Here I'll give all the solutions in terms of the free variable z, but I'll label it as t. So keep in mind that it is not a particular number, it is a free variable. And then I backsum. Okay, so 3y minus 6z equals 6, that becomes 3y minus 6t equals 6, which means 3y equals 6 plus 6t. And then divide both sides by 3, and you get y equals 2 plus 2t. So z is just t. Y is 2 plus 2t. And then we back sub one more time. X minus y plus 5z equals negative 2. That will become x minus, what is y? Y is 2 plus 2t. Plus 5z, what is z? Z is t, so plus 5t equals negative 2. And solve for x in terms of t. So this means x minus 2 minus 2t plus 5t equals minus 2. If you add 2 to both sides and combine the t's, you get x minus 2t plus 5t is plus 3t, and negative 2 plus 2 is 4. So x is equal to 4 minus 3t.
Wouldn't that be 0? Because we're adding 2 to the negative 2.
Oh, maybe. Sorry, did I goof? Yeah, I need to add this over, right? Yeah. Negative 2 plus 2 is 0. 0. Thank you. So this is good. This is not good, right? So just negative 3t. Thank you. All right. That's it. This means we have our solution. So the solution here is the set of all ordered pairs x, y, z. X is negative 3t. Y is 2 plus 2t. And z is just t. And t is allowed to be any real number. So the previous guy, no solution. This guy, infinitely many solutions. minimize that whole last row. And this is how one solves linear systems if one doesn't want to fuck with matrices. But believe me, one wants to fuck with matrices. What's a matrix? Just don't write the letters. So I would write 1, -1, 5, -2, 2, 1, 4, 2, 2, 4, -2, 8. That's a matrix. And then you do all this same stuff, but instead of writing the letters, you just write the numbers, and you let the position remind you which letter is attached to each number. I'll show you the notation for that on Monday when we begin section 10.3 on matrices. I am going to, I think I already did, right? I told you about the homeworks. Yeah, homework 7 and 8 both due on Monday. Did I publish those both for you? Let's see, stay signed in. Yeah, okay, yep. So you're in good shape here. Just go ahead and wrap up the stuff that's in there. I'm not going to give you homework on this yet because I am expecting that most of this is review. But do make sure you have good notes here. Consider rewatching this video, especially if your previous algebra classes did not handle systems well. I know that some college algebra professors leave this shit for the fucking end and don't really do it right. Some of you didn't take college algebra or took it somewhere else, coming here straight from high school, whatever. If you haven't seen systems before, rewatch this video. Rewatch this video, make sure your notes are good. Make sure you understand the notation. And if you want to talk more about anything, I'll be in office hours for the next hour. Otherwise, I will see you on Monday when we begin talking about matrices. Okay?
Thank you. Bye.
Of course. Take care, guys. See you Monday.